You can go ahead, Paul.
All right, we're going to present a lecture called Beyond the Classroom, Process Chemistry. And what I really want to focus on is the idea that anything we do in basic research ultimately gives insight into technologies which can be translated into processes. And those take place in vessels. So that's kind of the icon for this presentation. We've selected a process vessel. And that's because a process vessel is part of a larger overall process. And so the question we want to ask ourselves is, how do we transfer a chemistry that we work on in the laboratory to an industrial process? So chemical engineers look at what's being done in the laboratory and they say, well, I want to convert that to a large process facility that might cost $500 million. But that's one way of thinking about it, but there's also the reverse way, which is we can imagine that anything we work on in terms of basic science will contribute to some chemistry or catalytic technology, and then that could be potentially scaled up. So what you want to think about is, how could I select the chemistry that I work on such that it could go through a design process and ultimately become a process technology? So one way to think about this is, what can process analysis tell us about chemistries to study? And how can it shape our thinking about what type of fundamental research we do? Now that's a very big question, and I'm going to go through the process of design, the red arrow right there, and then I'm going to use at the end of this the insight we get from that to think about the actual selection of the process chemistries. So the process development has both scales and times, and so we start at the left with a lot of what we do at the university, where we do fundamental research. We work in flasks, beakers, very small scale systems. And while we don't think of it as at low cost, it's in the overall process development time, it is relatively low cost and low capital. You don't have to buy much equipment, and the time scales are relatively short, 1 to 3 years. If you have an exciting chemistry that looks promising on paper, you could then take that to the next scale, which we would say bench scale. We can do this in the laboratory. The costs go up significantly, so now we'd say it's moderate cost. But the time scale of this would be to build a process flow system that might still fit in a laboratory. It is still moderate cost, low capital compared to what would be the next scale, which would be the pilot plant. Now in this case, you're building a system that might run for 2 to 5 years, and now the capital investment becomes relatively significant compared to the bench or the laboratory scale. And here what you want to do is work out a lot of the challenges associated with combining chemistries and separations together, where you've invested significant money, but not nearly as much as you would at the commercial scale. So if there's a significant problem, you can find it there where the capital investment is relatively limited. Now ultimately, a pilot process that's successful and meets all the targets would go to a commercialization phase. And this will be 1 to 2 years of construction. At a lifetime, we say 20 to 50 years, but it could be 100 years. It could be even longer. It could be indefinite. A lot of process facilities run forever. Now in this case, the cost is very high, the capital is very high, and the risk to start one of these without going through the bench and the pilot scale is extremely high. And there are examples where people have skipped either the bench or the pilot scale facility, built a commercial scale system, and completely regretted it. So how do you get from the lab scale all the way through the bench pilot scale to the commercial scale? Well, you need to go through the design process. And here's an example of a process flow diagram. This is where we take a chemistry, in this case it's methanol catalytic cracking to gasoline. So you can see in the process flow diagram, you can see the methanol comes in, and then a bunch of aromatic compounds and olefins come out, such as benzene, toluene, octene, xylenes, etc. Now, the way this is conducted is through what we call unit operations. Every reaction or separation or change in pressure or temperature occurs in a unique vessel, which we call unit operation. This includes reactors, pumps, compressors, heat exchangers, distillation columns, flash tanks, and some things that aren't even shown depending on the type of process flow diagram you look at. In that case, some diagrams have valves, and there are just thousands of valves, and other cases not. The question is, how do you think about all of these designed individually, and then how do you put them together? This is where I want to come to the overview of the entire presentation. First thing you have to know is, what are the unit operations? And this is where the chemistry happens, so we have to be able to describe that. Part 2 will be about, once we know what the unit operations are, how can we put these together in a way that makes sense in terms of the overall chemistry? And number 3, you can imagine just looking at this one option for a chemistry of methanol to gasoline on the right, that there are thousands or millions of possible configurations and designs. And you want to think about, how do I get the one that's the best overall, whatever that means. So let me start at the beginning here. And the obvious place to start is with reactors, because this is where the chemistry happens, and it's one of the most dominant unit operations in an entire process. And so how do we think about commercial flow-scale reactors? And we can actually think about them quite simply. Here's an example of one, and in this case, a reactor is just a tube. You have component A flowing in. It exhibits some complex velocity distribution. There might be heat transfer. There might be mixing of some kind. And then it comes out the other side where some of the A is being then converted to B. Now, a system like this we think of as an extreme case because the material coming out the backside of the reactor doesn't interact with the material coming into the reactor in any way. On top of that, you can have some temperature change depending on the exothermicity of the reaction, whether we have heat transfer equipment involved, whether we have mixing equipment involved. That's where the complexity comes from. Now, the opposite version of this would be something like a tank reactor. And in this case, we have a mixer that as soon as A comes into the reactor, all the components are mixed very quickly together, in which case we have a very sudden change in the concentration, and the material leaving the reactor was very recently interacting and mixing with what's coming into the reactor. So here we can have rapid changes in the concentration profiles. We can have a very sudden change in the temperature from what comes in to what comes out. So this is really the other extreme of what we can think of for reactor design. So in terms of unit operation of reactors, I can put almost any reactor on a one-dimensional scale, all the way from almost zero mixing in a straight tube to all the way to a completely mixed system, something like a mixed tank. And of the thousands of different reactors for different applications out there, I can really put these somewhere on this degree of mixing scale. On the far left, this is a very famous reactor called the riser reactor for fluid catalytic cracking. The reactants flow from the bottom all the way to the top in a straight tube. What comes out the top doesn't really mix with what comes in, and then the catalyst can be recycled in a loop. That's different than something like a fluid bed reactor here in the middle, where what comes in and what goes out is sort of being mixed together in a fluid operation of either a catalyst or other solid material of some type. Now, even more extreme mixing is something like a fermenter, where everything is mixed together, and any one time, any fluid element has a high probability of interacting with any other fluid element. Now, all the elements that go into the design, you can take an entire course in all the aspects of mixing, heat transfer, chemistry, etc., but they all fall along some sort of description of this type. Now, once we make a product mixture, we then have to separate it back out. And so there's a large number of unit operations for the different types of separations that have to happen. And one that's very important is just the first idea of a flash tank. So material come out of a reactor, they go into a vessel, in this case 121. The light components go out the top and the heavy components come out the bottom. And I can pick the temperature, the pressure, and the holdup time in that vessel to do that very effectively. This is most commonly used if you're doing something like a hydrogenation with hydrogen of something heavy, and the liquids just readily come out the bottom with negligible vapor pressure, and the hydrogen just naturally comes out the top. It very quickly gets a nice separation of heavy and light components. Now, you can imagine that one stage is never enough to separate a complex mixture, and so what we can do is stack many of these equilibrium stages on top of one another, in which case my feed mixture will come in, it'll go into a stage here where our gas and liquid, vapor and liquid will equilibrate. The vapor will continue to move up, and at the very top it can be condensed, and then some of the liquid can be returned as reflux and come back down the column, and this can continue with vapor always going up and liquid always coming back down. And when I do that with multiple equilibrium stages together, I can take a fraction of that condensed material off the top as my distillate with high purity, and I can take a fraction of the liquid coming down off the bottom as my bottom's material, and as higher concentration. So now in this case, this is the process of distillation. You can see a couple of distillation columns here in the picture. There's a large number of design aspects to this, such as how much of the reflux do I need to return to the distillation column. I'd like to return as little as possible since I'm essentially losing that material. The size of the column, the amount of flow, the temperatures, the number of stages, and the type of stages that all go together. Now, there's been a lot of work done in designing these. The most famous simple approach to think about this is the McCabe-Thiele diagram, where I can look at the equilibrium concentration between the liquid and the vapor phase as a function of the fraction. And what I can actually do is figure out where my concentration of mixture comes in, and then I can count off as a crude estimate of how many stages I would need to get either from the bottom to the top, and use that as the first estimate for how many stages I would need in a distillation column. And from there, I can go to much deeper questions about how efficient it is, how many flows I need, etc. Now, there are other types of separations that are really important for process chemistry. You can imagine a system where I would have synthesis gas like hydrogen and carbon monoxide with a bit of something like H2S in it, in which case I don't want to do distillation because I don't want to condense all of this, and it might be a very small impurity. I can use something which is called an absorber-stripper combination, where the gas will flow in, the H2S will be absorbed into a liquid. It'll then be carried out in this liquid to another vessel called a stripper, where I flow in something like nitrogen that pulls it back out of the liquid. And now I have a stream of purified H2 and CO, which I could use for something like methanol synthesis. And on the right, I have a waste stream, which has my waste H2S. And again, there's many design elements here of the temperature, the liquid I would use to circulate, the temperatures, the pressures, etc. So there are many other ancillary devices. Pumps are a big part of these types of facilities, and they come in many different types. There are hundreds of types and many different brands, and I'll just show you 3 very different types. This is a centrifugal pump you see over here on the right. You have a spinning head here, which imparts fluid head through velocity, which then converts to pressure coming out of the volume right here. A positive displacement pump is very different. This is a gear pump where I have fluid come in. It's then forced around by the gears and then comes out the top. These are used for different applications depending on what I'm trying to achieve. Something more relevant to polymers would be something like a Moino pump, where I have this kind of curved blade right here that turns. It's useful for very viscous mixtures. Now, how you select a pump, what size, what type of pressures you're looking for can be done using pump curves. It's a much deeper discussion, but these are critical to any process. Now, something that might be very surprising in terms of a process design is actually gas compression. You would think that this is very similar to a pump, but in terms of cost, compressors can be very expensive, both in the purchasing, but also in the application in terms of electricity cost. And that has to do with the inefficiency actually of compressing a gas. So a lot of effort goes into compressor design. In this case, you can see a multi-stage compression system here on the left, and we can use this very simple symbol to identify that. Now, because the cost can be very high, you can imagine if you're doing something like high pressure hydrogenation, high pressure hydrogen is very expensive to create. So we're looking for any sort of efficiency gain we can get in making high pressure hydrogen from low pressure hydrogen. And one way to do this is to do multi-stage compression, where we'll have one compressor, then we'll cool our gas coming out, then we'll compress again, then we'll cool, etc. And you can imagine the most efficient way to do this would be have an infinite number of compressors and interstage cooling, but then the capital cost gets too high. So we're going to come back to this idea of there's a balance between the cost of buying equipment and operating equipment, and there has to be an optimum number of units in a row that would be effective. But a lot of times you see these in stages of 2, 3, 4 compressors in a row, and after that it gets to be too much equipment. Okay, now another part, and just to include this, is that there are just thousands of valves in any process you go into. These don't add too significantly to the cost, but they do add up, and they do add a level of complexity. And any person that goes into work in a process system will see just hundreds of different types of valves, and they all have a specific application depending on what they're trying to achieve. Okay, so this brings us to the point now we have an idea of a small number of process unit operations that we can use to achieve different things, whether we want to have a reaction, separate condensable things, or separate gases, etc. And so we've come to the question of how we synthesize the actual process. There's a very simple question: how do we combine the unit operations together? Which unit operations do we select? How are the unit operations designed? How do we select the order of the unit operations? What are the combined unit operations such that they are optimized? And then, of course, when I keep saying what's better or worse, the question becomes what metrics we even use to determine whether something is better, or ultimately whether of a set of possible designs something is optimal. These are very big questions, and I'm going to address them coming up. Okay, so the question becomes, how do we synthesize a process? How do we put these different units together? And I'll start with an example here. If you have a mixture of 4 compounds, let's say a very simple mixture, N-hexane, N-heptane, N-octane, and N-nonane, and you want to make pure streams of each of these, how would you do it? Well, you can imagine that the mixture might come into the first distillation column, vessel 121, and you could split this where hexane and heptane went up the distillate, and octane and nonane went out the bottoms here. Then each of those went to their own distillation column, where we then had multiple trays and separations, and we had pure streams of N-octane, and then nonane, heptane, and hexane. Now in this case, you can imagine all the decisions you would have to make. You'd have to design each distillation column for that particular split, So temperatures and pressures, types of trays, condensation, reboiling, etc. But there are even bigger questions which you have to address, which have to do with how we put the units together. And so for a system like this, you can imagine 3 options. There are actually more options you can imagine, but I'll just pick these 3. You can imagine the first option, which I just showed you on the previous slide in this simplified diagram, or you can imagine where I always take the products off the bottoms, the first 2, or I could have option 3 where I always take the products off the distillate except for the last column. So the question is what I alluded to earlier, how do you know which process is the best? What's better? And what metric do you use? And what you don't want to have is 4 or 5 different metrics, because then you have to weigh the value of one metric versus the other. And so there's a very simple metric which we use, which we don't commonly think of in basic research, but is very common in development work, which is some sort of economic metric or economic potential. And so this becomes very important to think about how do the different design considerations show up as some sort of economic potential value. And the complexity here comes from the idea that some of these are one-time costs and some of these are yearly repeating costs. If you take a simple distillation column, for this to run a reboiler, you're going to need steam. To run a condenser, you're going to need cooling water, and for any pumps or valves or compressors or anything like that, you're going to need electricity. And those are going to be continuously applied each month of production. But there will be capital costs such as pumps, condensers, boilers, distillation columns, a lot of steel and equipment, which you'll only purchase at the start of the project. So how do you take all this into account and compare one system versus the other? You can't compare just the operating costs or just the capital costs on their own. And so what we have to think of is some time-related economic potential. And the way this has been done for a long period of time is to consider some sort of lifetime for whatever you're going to do. And we show this on what's called the cash flow diagram, where we take into account all costs together over the life of the project. And positive cash flows are up, negative cash flows are down. Now, if we're going to put in a distillation column, this is not generating any revenue. So all of these are negative costs. The one in red here is our initial capital cost when we buy everything and install it. And then every year, the costs in blue are the operating costs for electricity, steam, and cooling water. And we can pick some reasonable length of a project, maybe 20 or 25 years, that we can account for this. Now, the other problem is that each of these costs come at different times. So I can't compare a cost in 5 years with a cost at 15 years. So I need some way to compare the costs over time. And this is done through a very simple idea called discounting, where I take the equation you see here on the bottom right, and I take the cash flow at any one time, divide by the interest rate to the power of n being the number of years. The question becomes, what rate do I use? And most companies have the idea of a minimum annual rate of return. Depending on the type of company, or if you're a growth company like Dow or BASF or Exxon, your rate is going to be much higher because your projects are expected to return more. Than a company that doesn't consider themselves a growth company, it might be 7 or 8%. And you can then use that equation to bring all costs back to time zero. So when I discount, cash flows later in time are worth less than cash flows earlier in time. And now all the cash flows are equal to the same amount of time, which is time zero. So I can just at that point add them up. So if I take all the blue cash flows and bring them back to time zero and add them up, I get the purple bar, which we call the present value. And when we sum them up, we call it the net present value, or NPV. Now what's great about this is I've now taken all aspects of the design, converted them to some economic potential, brought them back to the exact same period of time to a single number, the net present value, which I can use to compare all of my potential costs. So if I was to do that for these 3 scenarios, I could take each of these 3 ways of combining the unit operations together, figure out the operating costs, figure out the capital costs, and then determine the net present value of each of these 3 options. And what I would like to do is select the most positive net present value. Now each of these options here are costs for the overall system. So I want to pick the one that loses the least amount of money. And in this case, option 3, with a net present value of only losing $12.1 million, is much better than option 1 or option 2. So that allows me to select, if I'm only limiting myself to optimizing this particular combination, option 3. Now that's a very simple small-scale system. The question becomes, what happens when I think of an entire process? When I put every possible unit operation together and utilize it, my yearly cash flows better look something like the following. At time zero, I invest in my entire process. That's the initial capital investment. And I dig into a big hole here by putting all of the investor's money in this negative cash stream. Once I then start the process, I have a yearly cash flow, which at the very least takes into sales minus the feedstock cost, which had better be very positive, minus the operational costs and the taxes. So what will happen over time then is I'll make a lot of money back right away, and I'll make less and less money back over time when I'm considering the costs at time 0. So what I can imagine then is if I'm looking at this and evaluating in terms of the present value, in each year I regain more and more of the money back that I invested, and at some point I cross over to 0. This is called the payback period. In this case, I have a diagram which shows it at about 3.5 years, and from then on all the money I make would be a positive, such that at the end of the 20 years my NPV will hopefully be some large sum of money. Now the way to think about this is if this net present value, if I'd invested in this particular process at time 0, it would be the equivalent of somebody giving me that amount of money right now, but only would be over the length of the project. So what's great about this, I know it's a lot of details about economics, there's a lot more details that go into this, but this basic idea gives us a single metric that encompasses all aspects of the design. And so from an optimization perspective, I now have an objective function that I can apply any variable I want to and tell whether it's an improvement or a negative. Okay, so the question becomes then, using this objective function, we can come back and ask ourselves, we know if something is better or worse using this economic potential, but now I actually have to make the decisions of how I'm going to put things together. And I'm going by Jim Douglas's textbook. He says for any process you make, there's somewhere between 10 to 2 to 10 to 5 power of 5 decisions. So if you have to make 10,000 decisions for any process design, the problem becomes the problem blows up in size. You can really never achieve an optimal process, and this is carried very clear by existing processes, which every year continue to improve, even though they've been around 20 or 30 years. And so this gets into the idea there's a science of process design, but there's also the art that you learn over time to try to eliminate possible designs which are never going to be viable as quickly as possible, such that you can very quickly get into some sort of rigorous optimization approach to selecting unit operations and combining them together. But this has kind of led to process design being somewhat philosophical. How do you, of maybe 10,000 different process designs, how do you quickly eliminate the processes that just have no chance of being economical without risking the idea that you're eliminating processes that could turn out to be very good even though you don't initially see them? And I'm showing you two kind of philosophies. Many people have espoused these besides these two people. Dale Rudd at Wisconsin and many others have looked at this. But you can think of this kind of two ways. Jim Douglas at UMass Amherst wrote the textbook where he talked about a hierarchical approach. And he says we're going to approach synthesis by establishing a hierarchy of designs. And using that hierarchy, I'm not going to possibly eliminate something that would be very good even though I can't see it initially. So he starts very simple. He asks the question if it's my process batch or continuous. Then he says what goes in versus what out at level 2. Then he says within that I'm going to look at some recycle structure, which we'll talk about in a minute. And then ultimately separations, how do I design that? And finally I deal with energy. Lanny Schmidt espoused kind of a different approach where he said rather than outside in, I'm going to look inside out. And that comes from his background of being a physical chemist and a reaction engineer, where he said the reactor is the heart of the chemical process. Once you have the chemistry designed, it dictates everything. So step 1 should be design the reactor, then design the separation systems around the reactor, and ultimately in step 3, optimize the subsystems around the reactor or separation systems. Now, these are two ways of thinking, and nobody really does all of these by some sort of recipe approach, but it makes clear how complex it is to arrive at an entire chemical process. So the way to begin is the way Jim Douglas and Lanny actually both think, which is where do you start? You have to figure out what scale you're working at. If you're over 10 million pounds of product per year, you're going to be a continuous process. And you want to be large because you get economy of scale. The bigger your process unit operations get, the more you benefit from a surface area to volume ratio. You buy less steel per volume of processing volume, which means your cost per unit volume of product, or per gram of product, or per kilogram, actually goes down. So bigger processes should be more economical. Now from that, you can treat your process as a black box, and you can say, I have these components going in, A, B, and C. I have some selectivity and conversion assumed maybe from chemistry that I've known, and I have products D, E, and F coming out. And from that, I can start to at least calculate the economic potential based only on that chemistry that's known. And presumably, what you're making is more valuable than what you start with. And if the economics look promising, then we can begin the synthesis and optimization using our objective function of net present value. And that's where I'm going to go in part 3. Okay, so when we want to dig into the actual design and combination of unit operations, we have to think about optimization. So if you consider a simple reaction now, A goes to B plus C, B might be our desired product, and C is some undesired side product. You have to think about how you would actually design and operate a reactor. And you can imagine that you could operate a reactor at high or low conversion, depending on how big it is, how fast the flow rates are, what temperature, etc. But the reactor does not exist in a bubble. You have to be combined with some sort of separation system. So when A, B, and C, the unreacted A and the product B and byproduct C come out of the reactor, we have to separate in some way. And we're going to want to separate our target product B from C, so that's a separation cost. But we're also going to recycle A back to the start of the reactor. Now, if we think about this in terms of the selectivity to the desired product B versus the reactor conversion, you can look at the plot in the bottom right. And this is a classic figure that you'll see from most process flow reactor systems. At low conversion, you have higher selectivity than you have at higher conversion. Now, this introduces the challenge of you would like to operate a system at a high conversion, because when you operate at high conversion, you have less A to recycle back. If you recycle a lot of A back, it increases the cost by increasing the reactor size, because you're moving through a lot of A and you're not doing anything with it. So we're very interested in, from the chemistry and catalysis side, of what these reactivity selectivity plots look like. And different catalysts will actually exhibit different appearance. Some will very quickly go to very low selectivity at just moderate conversion, and some will never achieve high selectivity, but they'll maintain it out to very high conversion, the difference between catalyst A and catalyst B. Now, that's important because you want to think about the combined economic potential of putting these two systems together. And you can think of this kind of individually. If you think of the reactor cost on the bottom left here, as the conversion goes up, the reactor has to get bigger to allow for higher conversion, and the costs will go up. If you think of the separation costs, as the reactor conversion goes down, you have to recycle more and more of your unreacted feed, and the costs go up. So when you combine these two systems together, you're going to reach an optimum economic system, not at the lowest or the highest conversion, but somewhere in between. This is one of the most classic process optimization problems, the combined two-unit operations that do reaction and separation. And these will also be dictated by the catalyst that you pick and the chemistry that you pick. In this case, you can see catalyst A and catalyst B achieve a different optimum at different conversions, but also a completely different magnitude of NPV. In the case of catalyst A, where you have very high selectivity at low conversion and low selectivity at high conversion, this is a very common scenario where you might operate a reactor only at 15 or 20% conversion and recycle a lot of the unreacted A after you separate it. Now, I bring this up because a lot of the times the chemistries we work with, we're very interested in how they perform in the selectivity conversion scenario. I showed you the generic plot on the left, but here's an example of two published papers from the last 2 years. One is in the middle is the Baeyer-Wilger oxidation of a ketone to make a lactone. And you can see here, this is looking at several different temperatures, the selectivity of the lactone versus conversion. And you can see at very low conversion, 15 to 20%, you're seeing selectivity of 80 to 95%. And as you get up to above 80%, it's dropped down to 60%. On the right is the chemistry we've been working on in the CSP, where we look at the decyclization of 3-methyl tetrahydrofuran. And what got me very excited is that you can see that a lot of conventional catalysts have very low selectivity, 55%. And these phosphorus zeocyls exhibit very high selectivity of around 90%. But what's surprising is how far out it goes in the conversion system, where other systems will drop their selectivity significantly, especially for dying systems. This one goes out very far. And so from a process perspective, this is a very useful way to reduce the economic costs of your particular system, to operate at high conversion and high selectivity. So how do you think about the reactor cost? Now, this is a very important point for the chemistries that we work on. As the residence time gets longer, our reactor conversion gets higher, our costs go up. And that's just because we're going to have a bigger reactor. So we have to have some minimum productivity in whatever chemistry we work on for it to be commercially viable. And if you think a lot about conventional commodity chemical production, the residence time there is seconds to minutes. It's not hours or days. And so we can set a minimum weight hourly space velocity of somewhere around 1 gram of reactant produced per gram catalyst per hour. And if we're not above that, the reactors just become way too large to ever be commercializable. So we're interested in both the selectivity of the catalyst, but also the activity. If it doesn't meet some sort of minimum requirement, we need to operate at higher temperatures while maintaining the selectivity just to achieve a reasonably sized reactor. Now this brings us to the other part of that recycle problem is how do you actually separate things effectively? And this gets to the question of what type of separations we can pick. Whatever comes out of a reactor, it very frequently will go to a flash tank. We'll do a simple separation to remove the light components from the more condensable components. But from there, we have the more challenging question of how do we do something like gas separation? Now, gas separation is generally more expensive because you're using something like membranes or pressure swing adsorption to make gas products or to recycle gases back to the reactor. This gets a lot more cost effective when we get something that's condensable. So if we have something coming out of the bottom of a flash tank as a condensable, and it's somewhere in about the naphtha to the diesel range, or a little above or a little below, we can condense it, and in which case we can do distillation, which is actually much more cost effective. This actually becomes a problem again when we get to something really heavy. You can imagine separating something like fructose and glucose. Now neither of these are volatile, and they actually can be reactive. If you heat them up too much, we have to do something like adsorption, and that gets expensive again. So in terms of volatility, we like stable molecules somewhere in the gasoline to diesel range. Now this ultimately comes back to the problem we talked about earlier. If we're doing a lot of distillation and we have complex mixtures, how do we put these all together? And you can imagine that for the number of components that you have, it gets big very quickly. If you have a 2-component system, you only have 1 column and there's only 1 column sequence. For 3 components, you can imagine 2 different scenarios. But for actually 4 components, which we talked about earlier, there aren't 3 possibilities, there are actually 5, the 5 you see here on the right. That gets big very quickly. If you have 5 components, which is not uncommon, there are 14 possible sequences of distillation columns that you can put together. For 6, it goes to 42, and from there it becomes almost unmanageable. But it's very common to have mixtures of 10 to 12 components in real chemical processes. So how do we possibly approach a problem this big? Well, what we can do is use shortcut screening methods to find column sequences which are just completely unrealistic and throw those out very quickly, and very quickly on a spreadsheet get down to maybe 4 to 5 sequences of distillation columns which are somewhat manageable. And there we can use a chemical process flow sheet simulation software to do a rigorous design of something like a distillation column. There are many of these available. Aspen and HYSYS are 2 commercial ones, Pro2, GPROMs, and many others. And what these do is a rigorous simulation of a distillation column or a reactor or any process vessel you want to put together. Now, from that rigorous simulation, you can then get the costs of the reactor, the separation costs, etc., and then calculate the NPV for each sequence and then do a comparison, so much as we talked about earlier. That's a big undertaking to take for a reasonable chemical process separation. It can take months to complete. Now, finally, the last step is frequently how we design the energy, and this can be a big input in the process costs in every month. So reaction and separation at this point is usually designed. We know reactors, we know how we're going to separate with certain distillation columns. But you can look at any process flow sheet and see heat exchangers all over the place, such as this stream right here, where we're actually cooling stream 4 to stream 5. And so the question becomes, we have many streams that we want to heat up and many streams we want to cool down throughout the process. And so the question becomes, could we pair these together in a way where we take the heat from one stream we're trying to remove and add it to a stream we're trying to heat? And so when you put your process together, you can break this down into 2 separate columns. We can imagine on a temperature scale some process stream that starts at high temperature and needs to go to low temperature, and other streams that start at low temperature and need to go to high temperature. And we can partner these off kind of like a high school dance, put them 2 together, and then figure out what is the optimal combination to do this. Now, there are algorithmic approaches to do this, and you can then find what is considered a pretty good combination of process flow streams. even when you're dealing with a large number of possible scenarios. Now, there's kind of two extremes you can imagine here. One is that you don't do any stream pairing with heat exchangers, in which case all the streams that need to be cooled use cooling water, and all the streams that need to be heated use steam. The other extreme is that you've paired all the streams together in every possible conceivable way to get the most energy savings possible. Now, the problem is both of these scenarios have problems. Obviously, if you don't do any stream pairing, you're paying a lot of energy in both steam and cooling water, which is not realistic. Now, every time you pair a stream, you not only save double the energy because you save both the steam and the cooling water cost for that paired stream. Now, the other extreme, though, is also a problem. If you were to pair every stream just to give you an optimum energy balance, it would be unmanageable from a process side because you'd have to make sure all the streams were able to get from one point to another without affecting each other in the event of a disruption. So there's some combination that works out to be both manageable but also optimal in terms of energy savings. Okay, so at this point, you put together your entire process. You have your process flow sheet, which you can see as a diagram. You know all the details of each unit operation, like a distillation column, and you know the economics of the entire process on a cash flow diagram. And what you can do now is try to, over time, comes about from years of analysis, is evaluate each of the system components for their sensitivity to the overall economics. So what I could do is I could look at a process flow sheet like this, and I could pick out a few places that I suspect are very important to the economics, and I could pick 4 variables. And each variable then I could vary, plus or minus 5%, say, and then figure out how much changing that variable 5% up or down affects the NPV. That will then tell me how sensitive my system is economically to that variable. And you can see here from the diagram on the bottom left, variable 1 is very sensitive economically, and variable 2 less so but still important, and variables 3 and 4 seem to have very little impact on the economics. I can then use that to go in and play with the variables that are sensitive, and over time improve the process more incrementally. So there are other aspects that play into this, and I don't want to go into this too far, but the other issues here are that we're making a projection over maybe 20 years, and at least a payback period of a couple of years, maybe as long as 5 years. And other things that play into this are market forecasts, which are really beyond our control. For example, in the chemistry to go from 3-methyl-THF to isoprene, which I talked about earlier, there's volatility both in the sales price of isoprene, but also in the purchase price of something like 3-methyl-THF. And so what you can do is actually from your cash flow diagram is generate a mix of all possible scenarios based on the prices of isoprene, the product and the feedstock, and look at what the possible scenarios would play out in terms of what makes money and what loses money. And you can even then do a Monte Carlo simulation of all the probability distributions of prices to look at how likely it is that you would lose money. And this can go into a whole field of forecasting and economics. But what you'd like to do over time is start with a process that's not very efficient. Here's an example of a process I've worked on where we take glucose and we make paraxylene. Where we started out, we looked at a simple catalytic system that was way too expensive. It was almost $4,000 per ton. Whereas Petro-PX paraxylene can cost anywhere from $1,000 to $1,500 per ton. And over the years, as we improve the catalyst, we then upgrade our economic evaluation, and the costs come down as our catalysts improve to the point where our last update we did of this before we put in our next best catalyst, we were now approaching the point where we could potentially compete with petroleum-based paraxylene from a biomass-based feedstock. Now let me come back to the point I made at the very beginning and summarize and conclude the presentation, which is when we started this, we said that you can take a chemistry from the lab to a process application and think about what it takes to get to the process. But you can also think backwards, which is if I'm working on a chemistry and I'm doing some sort of fundamental science, what should I focus on and what is the impact of that for potential commercialization? And I've put together a couple of slides here of things that I think are key points that we can take away to think about in our research. Number one, the processes should be 3 chemistry steps or fewer. Now, this is not a hard and fast rule, but it's a simple way to think about how can I get from A to B as a product reasonably in something that could be commercialized. And you can think of this in terms of just the overall yield. If each step, if I'm able to get both the reactor and the separator for that step to be greater than 90% in yield, which means a very selective reactor and a very good separation system, and I cube that for each step, I'm getting an overall yield of just over 70%. Now, for a commodity chemical to buy and sell, that means I've thrown away a little over a quarter of the cost of the money that I've spent just buying the feedstock, which is significant. And the way people think of this is the figure on the bottom right. I'm selling something, a product price, higher than what I'm buying it at, which is the feedstock price in green. I'm losing some of my carbon in orange, which are my selectivity losses. I'm also paying to convert it through process costs. And what's left is my margin between my production cost and what I sell it for. And the problem being that these prices can fluctuate, which I said on the earlier slide, but really the difference between the feedstock cost and the product price gets driven down over time as processes become mature, and it gets harder and harder to be competitive between the two. And so what we need to do is reduce the process costs in purple and really minimize the selectivity losses. So this 90% number is kind of a rule of thumb, and 3 steps seems to be a good rule of thumb. Another thing that's very important, and this comes into the feedstock cost. If we think about what feedstocks are actually cost competitive, it turns out that it's very challenging to find reactants that we can use that will be cost effective, because those have to be also manufactured. And it turns out that in a lot of the chemical industry, only a few feedstocks dominate everything, and that's mostly ethylene, propylene, and aromatics such as benzene. Now, even with those, the co-reactants are also extremely limited. We can use hydrogen for reduction. That's the overwhelmingly dominant reductant that we use in commercial systems. Chlorine and bromine are commercial co-reactants. For oxidation, we might use oxygen or hydrogen peroxide. For alkylation, it might be methanol, ethylene, propylene. And for making nitrogen-containing compounds, it might be HCN. Now, this is not a limitant, but these are the dominant compounds because the feedstock costs are so low. And anything new that we would introduce as a co-reactant that's more exotic would be very difficult to commercialize. Now, another aspect that's really been growing in strength in the past 5 years, both from the NSF DOE and from companies, is the idea of process intensification. In the first sequence you see at the top, you have three systems: reaction separation, reaction separation, reaction separation. What I would like is to have a sequence where C and E are both volatile components that can be easily separated. But what would be even better, especially if I work with heavy things like biomass molecules that have a level of oxygen, is to intensify the process by combining reactions together. So if I take the red and the blue reaction as separation systems, I can combine those together into a single reactor, and now I've completely eliminated one entire set of capital investment, and I've completely eliminated an entire separation. Now this can go a long way, and we don't have to combine 2 steps. We can go 3, 4, or even 5 reactions all together in a single reactor system. And what's even happening now is a big focus area is reaction separation. There's an area of research that's focusing on what's called reactive distillation for actually several decades, and there's many variations on this, such as membrane reactors, where we can do reaction separation all put together. So let me kind of end with how we think about introducing new technologies, which is what we want to do if we have new chemistries. An existing chemical process, if we kind of put it up against a new chemical process, it's very daunting. And because you can imagine, if you look at the pictures, one is sitting there operating right now. And another one we say is a greenfield opportunity. We could go in there, dig it up, and put in cement and then steel, and etc. For the top system, the existing system, the capital investment is already paid off 20 or 30 years ago. And so anything we put in the ground has to have a huge capital investment on top of the operating costs. So it's not really a fair competition in that regard. For the system on the top, a lot of the operational challenges have been worked out. For example, if a separation has an impurity that we didn't anticipate, that can be a huge operational problem that's already been worked out. For a new process, there could be huge process problems that are catastrophic that we can't anticipate until we go through the entire bench, pilot, and commercialization procedure. And then finally, the process at the top already has a market for all of its products, and it already has sales and customers lined up. Whereas a new chemical or a new process would either need to take away their customers or their market, and you have no defined prices. So if somebody asks you what can be done. Now this sounds extremely daunting, and it is. It's also the reason very few things get commercialized. But what's exciting is that a truly disruptive chemical or material really can overcome all of these issues. It just has to be done under a multi-year program focused on commercializing these. And of course, you have to start with something that could actually be commercialized. So let me end it right there. Thank you.